Okay, good evening, everybody. This is Bob, AK6R. We're down here in sunny San Diego where it was about 75 degrees today. And in fact, we got our first rain of the season came in today. So it's going to be exciting. We're supposed to get an inch and a half of rain tonight. So we'll see. And let's see here. I'm going to share my screen and we're going to do a PowerPoint tonight. Everybody see that, I hope. Let's see.
Yes,
Yeah,
yes.
okay. Yeah. We're going to talk about multi-band end-fed antennas tonight. I'm going to sneak in a little thing about coax noise filters. A lot of people don't know about those and some other little tips and tricks. And maybe you'll have an aha meeting or an aha night tonight, learning something you didn't know before. And hopefully, if that's the case, and will enlighten you as far as antennas are concerned. Uh, all right, so it takes about an hour to go through this presentation. I'll take questions, and if you pay attention, there'll be some virtual prizes at the end of the talk. So let's see. It's here. Let me give you a little bit of background on Palomar Engineers. It was founded in 1965 by Jack Althouse, K6NY, who was also Kurt Sturba, by the way. That was his pen name for CQ Magazine and for World Radio Magazine. And he did that for about 30 years. And when we purchased the company, it was in a 10-foot by 10-foot storage area. And he had all the original engineering drawings from 1965, and they were all in pencil because he kept making changes to them, and he would erase the old schematics and print in the new ones. And so anyway, we took that company, had a lot of old stuff in it, and most of it was chairs and tables and some ferrites and stuff. And we completely reorganized it. I repositioned it, so to speak, as an RFI solutions company. And subsequent to that, we've now become an antenna company. Over half of our sales are antennas, much to my surprise. But anyway, our objective was to provide products that make amateur radio fun and more effective and enjoyable by people. I've personally, I've run about 3 public companies. I have an MBA in finance and 2 electrical engineering degrees out of UC Berkeley. And so I've done the business game for a long time. In about 2010, I retired for the first time. And then I said, let's go find a company and have some fun. And so I looked for an amateur radio company. Jack passed away, and my wife and I bought the company. It is a woman-owned business, and that we use that for getting military contracts and stuff. But we split the product line into basically 5 different areas. One is antenna systems, and we specialize in off-center feds, end feds, loops, and in terminated folded dipoles. We're very useful if you're doing ALE or anything with fast band switching. After we got into the RFI line, we started making one-to-one baluns and then Ununs and feed line chokes, and we pioneered coax nose filters about 12 years ago, I think. And I can't keep them in stock to this day. I sell so many per month, but they really work well. And if you don't know anything about them, we're going to show you a couple slides on that. We have RFI solution kits for hams, for household, marine, RV, boats, cars, you name it. And what we tried to do is put those into solution kits. So that if you have an HDMI TV, for example, and you're getting interference on it, or you have subwoofers, or a variety of other different types of things, or you're switching power supplies real noisy, we have a kit for each one of those items. You just buy the kit, you put the ferrites on. You don't have to know much about the technology behind the ferrites, but you just install it, and generally it effectively takes care of the RFI in or out of the device. We also have ferrite core products individually. You can buy rings, snap-ons, slip-ons, those types of things. And I go over a lot of that in my RFI talk. And by the way, this talk and the RFI talk and every talk that I've given for the last, I think, 6 years is on the website under technical information, speaker presentations. And you can download those in PDF format or in a slide format, just like you're seeing here. The last thing we did is we took Jack Althouse's Kurt Sturba articles, and we put the I think the first 40 or 50 in one book, and and those are all free downloads, by the way, and you can utilize those anytime you want to. And we also have a bunch of other downloads that are free too, about different radio topics and stuff. We distribute through Ham Radio Outlet, Direct, eBay, and we just picked up a new dealer yesterday, as a matter of fact, in Canada. He'll be serving the whole Canadian market. Now that we have tariffs in Canada, it's that people can save some money from us shipping it over there. We service the amateur, consumer, commercial, and the military markets. Just about all the communication bands across the United States that are run by the government have our ferrites in them, with a huge contract that we got about 3 years ago. All right, let's talk a little bit about end-fed antennas. And it's a fascinating subject. And I'm going to give you a short overview of feed points and what end-fed actually means. I'll talk a little bit about some real-life examples. And then we're going to talk about basically 3 types of end-feds. One is the resonant end-fed half wave. Very popular right now. It's got some drawbacks, and we're going to show you some of the other alternatives that you should consider when you're thinking about end-feds. The next one is a non-resonant end-fed long wire, and that's the 111-footer that the other guy was talking about before we started the talk here. And then the last one is the resonant end-fed, and we call it an end-fed off-center fed. And we pioneered that one about a year ago, and we've got about 1,000 of them out there so far. They've really turned out to be a useful antenna. Basically, not to spoil what's coming, but you get more bands and less space, and that's what a lot of people need. I'm going to show you some typical configurations that you can set up for all different types of installations, from portable or POTA and SOTA, field day for your own installation at your QTH, and just give you some ideas tonight. And then how to choose one that fits your needs for bands, space, and power. And then we're going to talk a little bit about feed line chokes that go with those, and coax noise filter, and one of the major problems that you may be having because you have an antenna switch, but it's solvable, and I'm going to show you how to do that. And then we're going to have a little Q&A at the end, and we'll award some virtual ferrite cups. Okay, so let's put our thinking caps on, and we're going to talk about antenna feed options. And basically, there's 3 types of feeds. There's center fed, which is typical of a dipole, and typically, depending upon the height of the dipole, can be anywhere from about 25 to maybe 120 ohms. There's the typical off-center fed, which means you're just not feeding it in the center. Sometimes you feed it with ladder line off-center. Sometimes you feed it with coax. And ours, we're going to talk about, is our coax fed. And depending upon where you choose that point, you can determine what the feed point impedance is. And then there's the one that you feed all the way at the end. All right. So, and typically these are half wavelength antennas. So half of them are a quarter wavelength. Well, the quarter wavelength inverts its impedance at the end. So it's 0 at the end, but I'm sorry, it's 2,000 to 3,000 at the end, and virtually no current or no impedance at the middle. So it takes a different type of transformer to match each one of these, and the 50 ohm coax. So let's go through some examples and give you some ideas and show you a few pictures. Here's a typical antenna, and this is kind of like a buddy pole. It's a long buddy pole, but here's the idea. And tonight we're going to be talking about antennas that cover 40 through 6 meters, basically wires that are about 66 feet long. Now, we make them for 80 through 6 also, and 160 through 6, but most people, I find just by looking at some of our sales records, the majority of people are buying 40 through 6 meter antennas in all different sizes and powers and those types of things. So, excuse me, here's a typical a regular old dipole, and it's got It's got two sides to it, and because it's relatively low, about 20 feet, you if you go right to the middle, you would roughly get around 30 ohms. But as you move the feed point from the center all the way to the end, remember it's about 2,000 down here. So somewhere's a little bit off center electrically, it'll be roughly 50 ohms, and you'll get a good match. And that's what Buddy Pole does with theirs. They make it electrically a different size by putting coils in theirs, and but each size is a little, physically it's the same, but electrically it looks like it's off center, and therefore it matches very nicely. And for those of you in the know, anytime you're using a coax fed antenna, you probably all know that coax has got three conductors, and the outside shield is actually an interconductor and a separate electrical outside conductor. And that's because of a concept called skin effect. And if you're not familiar with that, look it up, but basically there's three conductors. And so as you push the signal up through the center of the coax and it reaches the shield side, it says, wait a minute, I can go to the shield, or I can go right back down the outside of the coax. Or I can go to the dipole or the outside of the coax, unless you put a stop sign in there. And a stop sign is called a choke. And in this case, we're using 5 ferrite beads in a row. Not a really good choke, but that's just the way the picture was drawn. And it it works effectively for these really low dipoles. And so that's one easy way to create an antenna is just using equal sides, basically a half wavelength on each side electrically. So let's go take a look at something a little bit different but very similar, and that's called an off-center fed dipole. And here again we have the same 66 feet, but what we've done is we've taken 55 feet on one side and 11 feet on the other side, and then right around that match point. Okay. And by the way, this is a different offset than most everybody else uses. They all use 1/3, 2/3, and we're more like 83%, 17%. And I'll tell you the reason in a second. And you feed that with coax, go right down to your radio. And if you were using a coax noise filter, it would go here right next to the station. And we'll show you about that in a second. We have off-center fed dipoles for 80 through 6, 40 through 6, or 20 through 6. The 20 through 6s are used a lot by the Parks on the Air and Summits on the Air folks, and also to some extent the field day people. So let's just take a look at the SWR of this type of antenna. And that's on the next page here. So we have frequency going across the horizontal, and we have SWR going up here. And this is the 3-to-1 line right here. So if so everything below this is less than 3. And in fact, this is the 2-to-1 line right here. And this is the typical 66-foot wire off-center fed that we manufacture. And I've used these, and lots of people use them too. But you see, this is the SWR. SWR dips very nicely at 40, 30, 20, 17, 12, 15, and 10 meters. Most off-center fed antennas will not give you 15 meters, by the way, because they're 1/3, 2/3, or 66 and 33%. They will not give you 15 meters. So that's why we changed the point of the feed point, so that you would get 15 meters. And it just as a by-side, you also get 6 meters, because our baluns are so wide and broadband, because we make them different than anybody else. Now, the balun that is used on this particular antenna, I'm going to go back here, is a 4-to-1 balun. And it's got a 1-to-1 choke also in it. So you do not get that feed line radiation that you would if you were using a dipole without the beads on it. So it works very well. Like I say, we have quite a few of those out, and they work really well. So those are typical dipole type antennas, just fed differently. Well, the reason I go through this is because we're going to have an analogy between end-fed antennas and off-center fed antennas, and some unique things that we can do if we kind of look at it a little bit differently. So let's go over here. The end-fed antenna types we're going to talk about are the end-fed ZEP. All right, it was in the old Zeppelins, if you remember way back when, if you're that old like me. It's also called a J-pole antenna. We have the end-fed half waves, and a big contingent of people are using those now because they don't know about the bottom two antennas, the non-resonant end-fed long wire, and that's what the 111 foot he was talking about, and then the resonant end-fed off-center fed. And we started that, like I say, about a year ago, and it's just taken off like crazy because of the more bands with less wire, basically. So let's go through those. I remember being a novice in the 1960s, or early 1960s, and I tried end-fed ZEPs. I was trying everything in those days, but an end-fed ZEP is basically a half-wave piece of wire. It's got a very, very high impedance here, and it's fed, in this case, by a quarter wavelength transmission line. It really doesn't make any much difference whether it's ladder line or coax. If it's electrically a quarter wavelength long, and if you short one end, there'll be a point where you can go up and hit 50 ohms, whereas the feed point's going to be about 2,000 to 3,000 ohms. So this is the way they match those. They either make the antenna itself a horizontal, or if you made it vertical, it would look just like a J-pole. And then you're tapping it right up at the 50 ohm point here. You do have to put a choke in it because you got the same problem with shield common mode current. So you put that in there and that antenna will be fine. All right. It works sometimes, most of the time it's single band. If you make it for 40 meters, sometimes it'll work 15 meters, the third harmonic, but that's about it. It needs a feed line choke, of course, and typically a 66 footer, which is what we're concentrating on tonight, will work one or two bands, and that's about it. The next type of antenna is an end-fed half wave. All right, and this is one that we made for about a year because everybody was wanting those, and this was before I developed the new antenna, which is far better, which you'll see. But basically, a little transformer with a 49-to-1 transformer in it. So it was taking 50 ohms, multiplying it by 49, not quite 2,500 ohms. And it would see 2,500 ohms right out the wire here. You'd attach a half wave wire, in this case 66 feet, and you could work certain types of bands, which we'll see in a minute. However, they have to be harmonically related. There's no way of getting around that without fudging it with a tuner. So here's a typical installation. You would put the 49-to-1 high up on a tower, throw it over a tree limb, whatever it happens to be, and then you would stretch out your wire. It could be an upward sloper, a downward sloper. You could zigzag this. You can bring it all the way out, and if you don't have quite enough room, just drop it that way, all right? But typically, this is what they look like. And then there's usually a choke somewhere along here, and depending upon where you put it, it will tell you how many bands you're actually going to get, all right? So what's a typical SWR of our 66 footer? Okay, so here's what it normally looks like if you were to take a 66-foot piece of wire and and feed it at the end with a 49-to-1 or a 64-to-1. Some people use 64-to-1s. They get a little bit different SWR, but pretty much the same concept. So it dips at 40, it dips at 20, dips at 15, which is the third harmonic of 40, and you get a little bit of dip at 10. But if you look at it, there's nothing in between. There's no 17, there's no 30s, no 12s. And certainly because of the high impedance transformation, the 49-to-1, it's very difficult to get anything over 10 meters. And in fact, 10 meters, this is a very good 10 meters. Most of the 10-meter ones are way up here above 3-to-1. And the people have to use their antenna tuners to bring them back down. Now, The only problem with an antenna tuner is when you do use it, and you use it, for example, to tune 12 meters or 17. The Unun is sitting here and it's working its what off, but the antenna tuner tunes the coax so that it has a low SWR. But you really have to reduce the power that you're giving to the Unun, otherwise you'll blow it out very easily because it's doing all the work, it's doing all the sweat. Now, I want to make one thing real clear with this if you're not familiar with it. These are N-fed antennas. That means that they're voltage fed, not current fed. And what does that mean practically? All right, let's go to the next slide here. And I put together a slide depending upon whether you're using a 49-to-1 or a 64-to-1. And I said, okay, well, how many watts input do you have to put in? And what's the corresponding voltage at that feed point? All right. So if you're putting in 100 watts, there's almost 500 volts there. If you're just QRP, you got 150 to 200 volts, but you certainly don't want to touch that thing while you're transmitting. And worse, a lot of guys are using these for FT8 and for digital, which is high duty cycle, and they're running 1,000 watts. They don't realize there's almost 1,600 volts at that little junction there. And if they don't build their 49-to-1 correctly, it's going to arc out and possibly wreck the transceiver and linear amplifier and all that type of stuff. So just be aware that this antenna has got very high voltage at the feed point. So if you're building something for it or you want to do it yourself, well, just be very cautious. Or if you're using it in the field, like a field day operation, you don't want to have it so that kids and pets and stuff can touch that, because typically you're running 100 watts and you're going to have roughly 400 to 500 volts on that thing. We discontinued it and this was one of the reasons. We discontinued it because we came up with a safer, shorter, and far superior N-fed. All right. And I'm going to show you two options right now. First of all is the non-resonant N-fed. All right. And we have that all the way up to 5,000 watts, but basically it consists of the transformer. This is the 100 watter, and you're going to attach the wire right up here. All right. This is the 500 watter, and you can see it's already attached here for you. All right. And it typically comes in lengths of either 40. We offer lengths of 41, 71, 111, and 155. And in fact, we put a 173 on there now because a lot of guys like to do AM broadcast, shortwave listening. And the 173 picks up the AM broadcast band, if I can say it right correctly, very, very well. And it really helps on 160 also. And so you need three things. You need the matching transformer, the wire, and then you need a choke. All right, and I'm going to tell you about the choke in a second. A typical setup looks very similar to the N-fed half-wave, but our most popular one is our 71-footer. And like I say, there's probably at least 5,000 of those out. And we sell a couple hundred, maybe 200 or 300 a month. So it's a very popular antenna because it's very easy to put up. All right, like I said before, configurations are approximately the same. You can make them vertical, you can make them L-shaped, you can make them U-shaped. You can zigzag it up and down, or you can slope it down or up, and you can also zigzag it. I have people that put these, I have a lot of people in Florida at the retirement centers, and they put them up along the sideboards of their roof so that the homeowners can't see them. And they're 71 feet of wire, and then they run the coax internally to their shack. But there's a trick here that you need to know. The 71 feet of wire here is going to radiate your signal. But also the wire, the outside of the coax from the matching transformer all the way down to the stop sign, otherwise known as a feed line choke, is also going to radiate. So if you have it on the side of a tower or you have it vertically, you're going to get a nice DX low angle radiation from your coax, as well as the radiation from your wire. Okay, so the total antenna length is the 71 feet here, or 111, or whatever it is you're using, and the length of the coax here. So in this case, it's 71 plus 42. The entire antenna is 113 feet long. And we have chosen a feed point where the impedance is roughly such that you're going to get a SWR of typically less than 2 to 1, in some cases less than 3 to 1. You can work 80 and you can work 60, and the coax radiates just like the wire does, but it's not resonant. It's a non-resonant antenna, and that's one of the things that makes it work. So let's take a look at a typical SWR graph of what these antennas look like. So this is the 71 footer. This is the 3 to 1 line up here, the little green line. And the 2 to 1 line is right here. And you'll see that just about all the bands, except 30 is a little bit higher, and 20 is 2, but all the other bands are pretty much under 2 to 1. And even 80 meters, virtually all of 80 meters is under 2 to 1. So here you have a 71-foot piece of wire. You're going to have the coax anyway. And so why don't you utilize the coax as part of the radiating antenna? And that's what we decided to do about 5 or 6 years ago. And this antenna is proved to be very, very popular. If you go a little bit longer in antenna length, all right, and I think on the next page we have one here. This is the 155-foot antenna. Now the choke goes at the 95-foot mark on this one, so you have to have at least 100 feet of coax, typically 100, 150. And you put the choke at the 95-foot mark from the impedance transformer, and then you get this. These are the bands that you get. Remember, this is 3 to 1, but if you look at the 2 to 1s, for virtually all the bands with the vertical columns in them, virtually all the bands are under 2 to 1, all the way across. You don't even need a tuner out here. The thing tunes. 6 meters is also the same way. I just don't have it on the graph here. But look at that thing. You virtually can work all the bands, 80, 60, 40, 20, all the way to 6 meters with just one antenna, and you can work the world very easily. Now, I'm going to give you one, and so this was an example of a non-resonant. Okay, and I'm going to go back a slide here, right here. If you think about it, you have an impedance transformer, you have a wire here, and you have a choke. What is this technically? It's an off-center fed dipole. It's a non-resonant off-center fed dipole is what it is. And it requires a 9 to 1 transformer to make it match nicely. Now we're going to take you one more step, and that is we're going to use a resonant antenna. Again, we're all talking about 66 feet here, but if you wanted an 80-meter one, it's going to be, the wire is going to be 95 feet with a choke at 40. If it's a 20-meter one, it's 25 feet long and the choke's at 7. For the one we're talking about here, remember the off-center fed had 55 on one side? Well, let's just get rid of that extra 12-foot wire on the off-center fed dipole, and instead, we're going to use 12 feet of the coax. So what's the configuration? This is what it looks like. It's 66 feet from the antenna wire plus the 12 feet here. It's actually 11 feet, I think, 11 and a half feet. That is the 66 feet. But because it's, let me go back, because it's resonant, the impedance here will be approximately 200 ohms. Non-resonant, it was approximately 400 to 500 ohms. So this one here allows you to, again, configure it as up-down slopers, inverted Bs, however you want to do it. But it's it gives you, again, the other nice thing about it, of course, is that this is current fed. There is no high voltage here like there is with the end-fed half wave. All right. It does require a choke, and we supply chokes with all of our antennas. very easy to use. This is an example of a choke. It's like a clamshell. You take your coax, in this case RG8X, put it through about 6 times, clamp it shut right at the 12-foot mark, and bingo, you've got some great SWRs, which I'll show you right here. All right, so here we have a 55-foot piece of wire versus the 66 that the end-fed half wave is. But guess what? I get all the work bands now. And the balun, or I'm sorry, the Unun is not breaking out of sweat at all. I can run full power on these things. I don't have to back it off because being non-resonant in particular bands. I get all the bands, including 6 meters, by the way. Our 4-to-1s are actually good from about 1 megahertz almost out to 100 megahertz. They are just virtually flat. It's because we make them differently than everybody else does. We use bead technology. We do not use toroids. And the wires are much, much smaller, much shorter. I'll just give you an example. Our 1-to-1, our 4-to-1 100-watt one only uses 9 inches of wire with a single turn primary and a single turn secondary. That's all you need to make this happen on your wire. It's very, very simple. Low cost to make. We keep the prices down. And we get tremendous results because they're so broadband. All right, so let's compare these two antennas. This is our 55-foot wire, all right? And I'm going to compare it now with the 71-foot wire. And I'm going to compare it, basically these were set up as slopers, upward going slopers to a tree. And I think the matching transformer is roughly 10, 15 feet off the ground. So the end-fed, the 55-footer, won't really work 80. However, it works the other bands a little bit better in some cases than the 71-footer. All right. So depending upon how much room you have. So in this case, remember it's 55 feet of wire and the choke goes at 12 feet. So you can have a smaller length, a coax length. All right. And this is very useful for guys that are doing parks on the air or they're doing portable or field day operations because the length of the coax doesn't have to be very long. However, if you choose a 71-foot piece of wire and you have a coax that's at least 50 feet long, you can then work 80 meters, and some of the other bands have a little bit better SWR, but still they're all in the under 2-to-1 range, and it's a very, very useful antenna, simple to install, and it just depends whether you want the extra band or not. All right, so very, very popular in both ways. All right, so let's compare all these guys. All right, I made a little chart here, and this is the end-fed halfway we were talking about before, the 66-footer, the non-resonant end-fed long wire, the end-fed off-center fed, which is the 55-footer, and then this is the regular off-center fed right here, which has got both wires. All right. There's no counterpoises on the off-center fed because we're basically taking that 12 feet and putting it on the antenna. You can work 80 and 60 with these, and all the other ones, the end-fed halfway, you only get 1, 2, 3, 4 bands. So I've got 66 feet of wire, 4 bands. But with the other antennas, I've got 5 feet more here, but I can work all the bands. Can't work 160, but I can work everything from 80 all the way down to 6 meters and vice versa. With 55 feet of wire, I don't get 60 and 80, but I get all of these, and I only have to have 15 or 20 feet of coax. In this case, I have to have about 50 feet of coax. So you can see it really depends upon the situation that you're in. By the way, all of these are low voltage at the feed point. All right. Doesn't mean that you shouldn't keep them away from kids and pets and those types of things, but you're not going to kill yourself if you're running a lot of voltage or you're trying to make it yourself and don't do it correctly. This has got very high voltage on it. Okay, so that's basically the differences between the three. And so I'm going to go. Our philosophy is no 49s. We don't like to do 49s for all those reasons. We think the resonant end-fed, off-center fed is a really good antenna, but a lot of people still use the non-resonant one because they want a longer receive antenna, like the 313 feet that the guy was talking about. Okay, so what are some of the secrets? How do you set these things up? Where do you get the parts? All that type of stuff. So how long is it? So if you're doing a non-resonant end fed, the two most popular lengths are 71 feet and 155. And the coax has got to be at least the choke is at the 95-foot mark here, the 42-foot mark here. Now, I've had a couple of people that um, uh, W6CBA and some other guys who run in their mobile homes, and they have 28 feet of wire and a choke at about the 16-foot mark, and they can work all bands 80 through 6. They got to use an antenna tuner at the radio, but they can work them all with even a shorter one than this. We haven't tried that yet or validated it, but I get reports back from people all over all the time of different lengths and what works and what works and doesn't work. And but our most popular ones are 40, 171, 111, 155, and now the 173. The end-fed off-center fed, remember, this is the resonant one. Like I said before, one works 20 through 6, 40 through 6, and 80 through 6. These lengths are significantly less than the lengths of the end-fed half waves. And you get all the extra bands. So why wouldn't you do that? I just can't figure out why people are struggling with 49 to 1s and all those fancy impedance transformers when all they got to do is wake up and find out that an end-fed off-center fed is a much better antenna. As we said before, you can make these vertical, you can make them horizontal, you can use L-shaped, you can bring them up, bring them down, upward sloper, downward sloper. Doesn't really seem to make too much difference. I have one fella, I have two people in New York City on high rises on the 29th floor, and they run them down the hallway of their apartments. They have the 20 through 6 meter one, so it's 25 feet of wire, a choke at the 6 foot mark, and they're working all over Europe and the United States with those antennas. They got good height, obviously, but they can't put anything out the windows. And now they're back on ham radio, and they call me up and say, thank you, thank you, thank you. I can get on the radio again and not not pay the penalty. Some of the things about SWR are really what determines the SWR, and will you be close to the graphs that I've been showing. It doesn't seem to make too much difference as long as the wires aren't crossing over each other or running underneath each other. You can do them as in, like I say, inverted L's, flat tops, you name it. The feed line choke has to be at the place where we tell you, plus or minus maybe a foot, depending upon, the the height and those types of things, but they're usually pretty close. Sometimes you need a coax noise filter. We'll talk a little bit about that in a minute. You can top feed them or bottom feed them. You can bring the matching transformer all the way to the ground, but then the coax is laying on the ground typically, and that's like laying half your dipole on the ground. Why would you want to do that? Take it up as high as you can if you can, or at least separate it so that it's got a little bit of height to it. You can run it through your attic if you want. You may have some issues with RFI because you got an antenna so close to some other things, but we can also take that into consideration with some of our RFI kits. I keep at least 3 feet away from metal objects, masts, gutters, those types of things. Now, I don't know I think everybody knows the difference between a balanced and an unbalanced and an unbalanced to unbalanced. These are all unbalanced to unbalanced. They're called Ununs, all right? And the non-resonant end-fed long wire, like I said before, is roughly is a 9 to 1, and it matches 33 to about 100 ohms with SWRs less than 2 to 1. So it's got a pretty good range, and if you pick the match point correctly, like we have, and I've shown you, you'll get very good SWRs. The end-fed off-center fed, which is a resonant antenna, their impedances at the point where we're matching them is typically 100 to 400 ohms. And that will give you an SWR less than 2 to 1 over that range. So they're a little bit different matching because of the resonant versus non-resonant, right? We have them in different power ratings: 100 watts, 500, 1500, and 5,000. And in the last 3 or 4 years, people have really gone nuts on QRP and POTA and SOTA and all those types of things. So I was quite surprised that we sell more 100 and 500 ohm ones, or we sell 5,000 ohm ones, or 5,000 watt ones rather, than any other antennas. It's either it's really low or it's really high. There doesn't seem to be too much in between. By the way, our duty cycles on our products are much higher than MFJ and some of the other ones that are out there. In fact, we do publish them. All right. So let's go. So here's some examples. Say you got the wire, you want to make them yourself. Here's a typical 9-to-1 500 watt. Here's a 9-to-1 that's 100 watts. Here's a 1500 watt. And if you really want to go big, we make them in a box because it takes more ferrites. This box here probably weighs about 2 to 3 pounds, but it'll take 5 kilowatts PEP. I'm a former RTTY contester, and I'm used to running 1500 watts RTTY, 90% duty cycles, and I have no problem doing that with the 5 kW at all. In fact, I could probably run about 3,000 watts with that. In fact, I probably have, not looking back at it. So we like to make our duty cycles high. And in fact, somebody called me the other day and they were running about 700 watts through my 500 water. And they wanted to know if they had to be concerned. And I said, is it warming up? He said, no, it's still working fine. It's because we put a lot of extra ferrite in them, and we use different ferrite mixes that nobody else uses. We use mix 61 for all of ours, and we use beads. We don't use toroids, and we have very, very short transformer windings. And that way, the bandwidth is much, much better. All of these do require a feed line choke, and depending upon the size of coax you're using, I run about 1,000 to 1,200 watts of FT8 all day long on my antennas, and I'm just using RG8X. All right, it doesn't heat up at all. So what if I lose maybe 1 or 2 dB on 10 meters? Doesn't really make too much difference. If I want to use the bigger coax, I have to go to a much larger ferrite, a big 4-inch ring, and then I got to put multiple turns to it. Although you can do it either way. So, like I say, most of our sales are for people that are doing 100 to 500 watts, and they use RG8X or small coax. RG58, for example, works just fine too. So, some of the give you an idea of costs and those types of things. These are roughly about 130 bucks for the 71 footers. You can buy the individual parts yourself. This is a 1500 watt, 500 watt. They're $69 for the 100 watt ones. The chokes themselves, $20. If you buy the complete kits from us, we give you the chokes and the transformer with whatever power rating you selected. So that's basically the transmit issues. I'm going to talk a little bit now about antenna noise issues, and I think we've all experienced this. And we came up with, like I say, it was about 2015, I think it was. I came up with the idea of a coax noise filter. And what is that? It's really just a really high impedance choke. And we did it, but we did it at the low level end. We started off with the 500 watters, and now we make them up to 5,000 watts. And where does that go? And what's the theory behind this? Okay, I'm going to give you a real quick lesson on common mode current here. If you're transmitting into an antenna, and at the end of the transmission line up here, all right, remember there's 3 conductors in coax. The signal that you're pushing up the center will also come back down the outside unless there's a stop sign there. In our case here, we don't want a stop sign. We want it to stop at a specific distance. However, if you have a beam antenna or you have a regular dipole or something else, you do want it to stop there because you don't want your coax to become part of the antenna. If you don't put a choke there, what happens is you change the length of the coax, and now your SWRs are going to change because it's part of the antenna. You've just lengthened one half of the antenna. All right, so you normally would put a choke at the feed point of this. But in this case, we put it at a certain distance so that the feed point sees a short side and a long side. Now, just the opposite problem happens on receive. All right. Down here at this end, when you plug in your coax to either your tuner or your radio, guess what? You're hooking up two receive antennas. One antenna, grounded or not, by the way, one antenna is the signal coming down the center. That's the one you want. But if you're running this coax through the attic or close to other noise sources, all right, or it's picking up noise from dishwashers, anything made by LG, for example, washer dryers, refrigerators, they put out a tremendous amount of noise through your AC power lines, by the way, and it's picked up by your coax. And so when you're plugging this in, you're picking up that noise in addition to the signal coming down the center. Now, you may or may not have this problem, but I'm going to take you through a simple test which will determine whether you have it or not. All right, so here's the test. And whether a coax noise filter will do you any good or not. In some cases, you don't need one. In some cases, you need it because your common mode noise level is S5 or S6. All right, so here's the test. First of all, turn your radio on, put it on, and we'll do this on every band that's important to you. All right, but first thing I want you to do is just unplug the coax altogether. All right, see if there's any noise. All right, if you're still getting noise, it's coming through another wire plugged into your radio. Could be a switching power supply that's noisy. Could be a computer interface coming through its power supply, which is not shielded very well for ham radio frequencies, or something else is getting into your radio. You got to fix that problem first. And typically you can do that with ferrites on those particular wires, and it will stop that common mode noise. And we have ferrite kits for all different types of radios, different models, you name it. We've tried to figure out the ones to use. However, in most cases, probably 80 to 90% of the cases, when you unplug your antenna, the noise will go away. So what does that mean? It means it's coming in through either one or two of your receive antennas. The first thing I want you to do is take your coax antenna and roll back the outside part of the antenna. And I just want you to put in the tip, only the tip. This is a crude test, but it works very well. Just put in the tip and measure the noise level. Let's just hypothetically say it's S1, all right? Now what I want you to do, the next step is screw in the outside and see if it jumps up. In a lot of cases, depending upon the route and the exposure of the outside shield to noise, it'll go up 3, 4, 5, 6 S units. Well, 6 S units times 6 is 36 dB, all right? And if you're constantly listening to that type of noise, all right, you can't hear the DX station who's weaker than that at all. And so with a coax noise filter in line, depending upon which one you choose, it can do up anywhere from typically 6 S units up to 10 S units. It will knock out, it'll suppress that common mode noise, right? Now, if you plug this in and you see no difference, then a coax noise filter is not going to do you any good at all. You don't need one, all right? But we'll talk a little bit about antenna switches in a second and how that can really drastically cause a problem too. But we have a solution for that as usual. So, okay, here's a plot of something called the common mode rejection ratio. In other words, that outside current, how much is it going to reduce it over a certain frequency range? So this is a graph of, I think it goes from 0.1 up to 60 megahertz. And at the low point, it's minus 38 dB. Well, what does that mean in the practical terms? It means that roughly 6 S units of noise is going to disappear at certain frequencies. But typically it's going to be anywhere between 4 to 6 S units of noise will be suppressed if it's common mode noise. All right. And this is on the 500 watt version right here, which is the most common one. We sell almost 300 or 400 of those a month. They're just crazy because they work so well. If you have more high power, all right, you're running 1500 watts, 5 kW or whatever, then those go down to minus 49. So they typically will have a lot better. And by the way, these go all the way to 6 meters. and they start underneath the broadcast band. So they're very, very broad. And I tell you, we pioneered these graphs for these types of chokes, and nobody does the same thing. They do not publish these. If you, I do a comparison on my website, comparing the W2AU and all the different types of one-to-one baluns and stuff, and you'll find that either they dip at one frequency, like 40 meters, and all the rest of them, they're useless. Or if you put one of these coaxial baluns in, all right, the coaxial chokes. The coaxial chokes are useless except for maybe a megahertz plus and minus from what they're designed for. And most people don't know that they're designed as a parallel tuned circuit. All right, coax has roughly got 28 to 30 picofarads per foot of a capacitance, and depending upon the width of the coil and the number of turns, that's a certain amount of inductance. Those are in parallel. And a parallel tuned circuit, by definition, it's got a high impedance at one end. All right, and so it'll have a high impedance at that frequency and that frequency only. All right, plus or minus a couple of megahertz, they're useless. So if you have a one band antenna and you tune it correctly, it will work just fine as a choke. But we don't do it that way. We put multiple beads in here with multiple different types of mixes of ferrites with different turns on each one, and we get a very, very broad feed line choke, right? So my caveat to you is, if you're going to buy a choke, do not buy chokes with no specs. It's like buying a resistor without any color bands on it. You have no idea what it's going to do other than it's a resistor, right? And most other manufacturers have not caught on to that. And gee, it's been over 10 years. So either they're trying to hide something from you or they're just copying somebody else's design. Okay, so where do you put these things? This is a typical example of a radio station. You have a transceiver, linear amp, antenna tuner, and antenna switch, right? We've already talked about the chokes for the antennas. If it's coax fed, you need a choke here to keep the transmit RF on the antenna and off of the coax. On the other hand, during receive, you need a coax noise filter actually, you're going to need it on the antenna switch, and I'll tell you why in a second, in order to choke off the current that's on the outside during receive. Now, in some cases, you have linear amplifiers, and I'll just tell you a fact that I've learned over the years is that all the RF from the linear amplifier doesn't necessarily go out the output. Some of it, because of its common ground, some of it will be fed back into the transceiver. It could be coming back through the push-to-talk line or the ALC. And so we developed a linear amplifier RFI kit for that. But in a lot of cases, it's just coming back on the shield of the input to the linear amplifier. So you would put a coax noise filter between the transceiver and a linear amplifier to get rid of that common mode current. Okay. Now let me spend just a couple of minutes here. We're getting towards the end. All right, so don't get impatient. What's the antenna switch noise solution, right? Here, and let me give you the theory first. All right, a lot of people aren't aware of this. Let's say you have an antenna. Let's say you have 3 antennas, right? And you selected antenna number 1. Now, what have you really done? All you've done is you've selected the center conductor of antenna 1. All the braids are all hooked together because they're all in the same piece of metal, and all the shields are hooked together. So here's something I found out the hard way. I have a neighbor with a solar system, and I have an antenna right close to him, probably 20 feet away, and all my other antennas are in the back lot. I have 3 acres here, and so I got all the other antennas in the back lot. However, before I figured this out, I had it all going through an antenna switch. In fact, this one right here, this has got 8 antennas on it, all right? And I didn't have any chokes in the coax before they went to the antenna. So here's what happened. I'm listening to a tri-band beam in the back lot, and the noise from the shield of the antenna that I have next to the solar system is coming in, and I'm hearing that noise, even though I have not selected that antenna. And the reason is it's being picked up by the shield, and there was nothing to block the shield as it came in here. So its noise combined with the noise of all the shields together, even though I wasn't using that antenna. So it dawned on me, this was one of my aha minutes many, many years ago, is let's kill that noise before it gets to the switch. And this is the way you do it. Here's a switch with two antennas on it. You put a coax noise filter into the line before the common part of the switch. If you put it in the common part of the switch, you're still, in this case here, you're still combining all three braids. Let's get rid of the braids. And so the only thing coming through the braid current or noise, so the only thing coming through is the actual signal that should be coming in off that antenna, and only this antenna. It disregards all the noises possibly coming in through all the rest of them. All right. And these are pictures of different installations. So in this case, I have chokes. In this case, they're the old style with the black caps on them. And there's 1, 2, 3, 4, 5, 6, or 7 of them. This happens to be a dummy load here, so I don't need one on that one. But this isolates all of the braids from all the antennas that are coming in so that I don't have to share noise between any of them or all of them, right? It kills it right there. And what I hear in the transceiver through the linear is just the signal coming off of that one antenna. Very, very useful thing to do. All right, I'm going to spend another 5 minutes here, and then I'm going to open it up for questions in a second. Typical RFI solutions, keep the antenna and coax away from house wiring, including AC power. Keep your cable satellite feeds clean. We have coax noise filters for 75 ohm cable RG6 type of feeds too, by the way, because a lot of people get into that. The telephone lines, all these wires can act as receive antennas, and they can overload your electronics. A lot of people have subwoofers and they transmit. Their AC power lines hook up, get the signal, and it transmits it into the power subwoofer, and it drives your wife nuts. Okay, use Palomar kits to solve these problems. And I'll just give you a couple of real quick examples. This is an ICOM 7300. It's got a shield. It's got a little choke here on coming in. Not a fancy one, but it's adequate for this particular need, but really should have a coax noise filter in here, and it would be about 10 dB or 2S units better. The DC power line has got a ferrite on it to get rid of any noise coming in off of your switching power supply. And then there are just regular lamp-ons here that go to the different aspects of different cables that you're using, computer interfaces, et cetera, et cetera. On the linear amplifier, AC line, DC, RF out, RF in, and the push-to-talk line. That's really all you need for a linear amp with a power supply built into the amplifier. If it's not, then you need a couple more. A lot of times you'll get calls from your neighbor, and you're turning on their alarm system, or their home theater system is picking you up, or you're getting computer RFI from your own house. Those types of things. I had one Army captain call me from Texas about 3 years ago. He said, "Son, I hope you got a solution for me. You're supposed to be the expert on all this." He said, I put a new radio in some of the airplanes that my pilots fly. And they went over this one particular condominium association, and all 100 garage doors opened up when they transmitted. And I said, okay, well, I've got a garage door kit. So he bought 100 of them, had his guys put it in, and the problem was solved. All right. Basically, the AC power lines and the signals from the door, all right, the wires coming from the door act as beautiful receive antennas, and they will pick up those signals and cause the falsing of the garage doors. Another thing to do with garages, by the way, if you put up LED lights in your garage and suddenly the key fobs for the garage doors don't work, what's happening is you're getting interference from the darn LED lights. So we came up with an LED light RFI kit that you put on the inside the light, if it's a strip light, for example, and that solves that problem. It gets rid of that noise. All right. So if you're a newbie to all this, you don't know what's going on, you can either give us a call or like all of our our products, we always give a code called a newbie 25. You get 10% off on anything you order. If you're a veteran, by the way, you always get 15% off, and there's a separate code for that. And just call me if you are a vet, and that's good all the time. And thank you for your service, by the way. With most of our items, you buy 9, you get 1 free, or you pay for 9 and you get 10 of them. Okay, I'm going to ask about 3 questions here. If anybody's got an answer, let me know. Otherwise, I'll just read it off. And so one of the questions is, what characteristic of a non-resonant, remember, this is a non-resonant end-fed, make it superior to a half-wave end-fed? All right, first thing is a non-resonant will work on even and odd harmonic frequencies. The half-wave has a complicated matching unit with high voltage. Non-resonant has simple matching unit and a lower feed point voltage. The non-resonant can work the work bands. The non-resonant antennas radiate as well as resonant antennas. Right? It's either all of the above, none of the above, none of the above. I have no idea. I was asleep during the talk. Anybody got an idea?
It's all of the above.
All of the above. You get the virtual prize. Number 1. If I was in person, you'd get a ferrite ring. That's how it works. Right.
Can always use them.
You can always use it. You got a virtual one now. Question number 2, where do you place the feed line choke on a bullet non-resonant 71-foot end-fed antenna? Right below the matching unit to choke off all the coax shield radiation. B, in the middle of the coax length to balance the radiation. You don't know how many people call me and ask me that question. On the coax at approximately 42 feet from the bullet matching unit, between the antenna tuner and the transceiver, end-fed antennas don't need feed line chokes. Anybody got an idea?
42 feet sounds about right. I'd have to look it up.
Boy, you got it right. You don't even have to look it up. Okay, 3rd question. One more after this. What's one of the best kept DX secrets in ham radio? Ladder line has more loss than coax. An antenna has to be resonant in the ham bands to radiate in the ham bands. All end-fed antennas work all frequencies, so buy the cheapest. Coax noise filters reduce common mode noise level in your receiver so you can hear more stations. All extra class hams go to heaven. Anybody got it?
It's D.
D is in dog.
Yeah, definitely not E.
I hope it's E. Okay, one more. Which company is your best source to end-fed antennas and RFI solutions? There's your answer. There's all our information. I'm AK6R Chief Engineer. And this presentation and the PDFs and everything are available on the website. I'm going to stop here and answer any questions you may have.
Well, I have questions.
Go ahead.
Yeah. And is it okay if I share my screen so I can use illustrations?
You can do whatever you want.
Okay, let's see. Select window or screen. Oh, come on. Why entire screen? That'll cover the bases. Okay. So as you mentioned in all your tech notes,
you're not sharing.
I don't know. I'm trying. What happened? Is it coming yet?
Yeah,
we got it now.
Okay. Well, I have a couple. This is a tool, a Python tool that Mike. I have to go back to this web page so I can get his name right. You may recognize this one. Yep. Mike. Boy, my computer is slowing down. Hey, I know whose page that is. Mike, AB3AP, wrote this cool Python script. Yep. He also has a C language one and one that he used MATLAB. And it's pretty cool because you can look at all this stuff that Bob talks about, avoiding the high Z lengths, avoid multiples of half wavelengths. This top graph, I was doing this for my 111-foot end-fed non-resonant today, one of Bob's Ununs. And I hacked the script so that I could look at my odd quarter wavelengths too, which are going to be your very low Z conditions, right, Bob?
Yep.
As you mentioned, you kind of want to be in the middle. You don't want to have a real high Z, or you don't want to have a really low Z, because then your 9-to-1 transformer won't handle it. So how important is this low Z? And here's an interesting thing. I just started using my 111 foot, and it's working great. But look, it even falls into the red zone a little bit. These red zones are the full band. And of course, things are even worse when I include the low Z red zones. So, Bob, can you tell me, how often is low Z really important compared to high Z, which is the high Z is the top illustration? And for some reason or other, sometimes we can kind of violate the principle, because your 111, which you recommend, I have up and running now today, and it's working great. Why?
So where is the choke on your 111?
Well, it's I can only tell you approximately, because it's actually, I haven't even had time to tune that yet. It's set where it worked really well for my 315 foot, and that is a totally, different length. I would estimate that it's at about 40 feet from the Unun.
Okay, so how long is your antenna?
The current one is 111 feet right
No,
here.
no, it's 111 plus 40.
Ah, yes, I got to add
Yes.
the 40. So we're at about 151 then, I guess.
Yeah, so what you want to do is make that total non-resonant.
Okay.
But it includes the coax. Remember, these are really off-center fed dipoles. They're just
Okay.
non-resonant off-center fed dipoles. And so what you're trying to do is find a matching point where all the bands are happy, but none is optimum. Okay.
Right.
And so by choosing that length for where the choke is, plus the length 111 feet, that particular length, 155 or whatever it is, will be, and if you choose those proportions, 40 and 111, for example, at that particular point, everybody's kind of happy, but nobody is optimum. All right.
Sure.
And in
But
fact, if you wanted to get fancy about this, you could actually put a second um, uh, uh, a second wire on the 9-to-1, optimized just for a specific band. And on
yeah,
that,
I had one on there for 315, but I took it off. I
yeah,
just haven't had time to optimize it. So would
yeah,
it make sense to rerun this program for total length instead of just the wire? And if that's the case, is the lower screen here, I added the low Z length capability to this Python script. Does it make sense to look at that too?
well, what they're measuring is the Z at the end of the wire, correct?
Well, yeah, that's how Mike intended this tool to be used, is look
Right,
at
but
the
that's
Z
not,
at the, yeah,
but that's at the end of that's at the end of a single piece of wire.
right, because
That's not a dipole.
right.
What we're
But
doing,
he
what we're
wrote these scripts for end-fed wires,
yeah,
non-resonant wires.
well, of course he did. But where is he measuring the impedance? He's measuring it right as if nothing else exists, only that one single wire.
Yeah, he doesn't really look at coax as being, part of the counterpoise system.
Well, you can make a non-resonant, off-center fed. And you just have to use a 9-to-1 balun.
Sure.
And you could have an actual short wire and a long wire, in fact, in the same proportions yours are, and just put a balun up there rather than an Unun. All right, because we're not, Unun allows you to use the coax, but you can have a non-resonant off-center fed with 2 wires on it. And in fact, that's what we're doing. We're just disguising, we're taking that extra 1 wire off, and we're just disguising the coax as part of that. And so the total length is an off-center fed. It's not just the wire. The wire, yes, itself per se is non-resonant, but we chose to put another wire with it and choose that feed point such that the feed point for the non-resonance is roughly in the 100 to 200, 100 to 400 ohm range for all the bands. Some bands will be high, some bands will be low. All right. And as a result of that, all bands, for all intents and purposes, are under 3-to-1. Most of them are under 2-to-1. And you're trying to adjust the length of that wire, all right, one or more wires, by the way. And that's why there's a stud on the side of the 500-watt ones and higher, because I have people that have used 6 or 7 different length wires to optimize each band. I mean, they went crazy. And what we're trying to do is just give you one length that works virtually for everything, but nobody's perfect, you see.
Yeah, well, within the range of the tuner, worst case.
Well, yeah, well, the tuner's just tuning your coax. The balun, the Unun itself is sweating if it's not seeing the right impedance. If you try to run a 40 meter dipole on 80 meters, it'll go nuts because it just can't fit it to there. All right. But if you play with different size length on each side, you'll find one that works fine with a 9-to-1 on virtually all the bands, with just a slight touch up from the 80 meter. 80 meter is just a wide band. And so you usually need to use a tuner, but not much at all. Did that answer your question?
Yeah, I'm just trying to figure out still how, if this tool that Mike wrote is useful for an end-fed non-resonant, but I mean that's using the coax. But you've got to use something, If you don't, the nature of electricity will find a counterpoise.
Well, exactly. And so he's measuring the length of a piece of wire, 105 feet or 111, whatever it happens to be. And at the end of that, because it's non-resonant, he gets a certain impedance. All right. But our antennas are completely different. They're really dipoles. There's two sides to it. And what you're trying to do is figure out, well, where is the point where the off-center fed has that impedance? And if there are other programs that are written, all right, and I don't have the call signs on top of my head, but they're written, and it calculates an off-center fed dipole and what its impedance is on different bands depending upon where it's fed. Well, I did a lot of study on those, and I found that if you use 66 and 33 or 34, which is what virtually all the manufacturers use, you cannot get 15 meters. But if you make it 80-20, guess what? The other bands aren't quite as good, but you get that extra band, all right, because of the differences in it. And so we kept changing that and tweaking it for different bands until we got to the point. I think our other one was 83 and 17. And now I get all the bands, and virtually they're all under 3-to-1, most under 2-to-1. And I don't have to play the game where, you don't get this band or you can't get the Warp band. But our antenna is 4 times more expensive than Palomar's. That's what's happened in the industry. And so I decided, no, let's just apply theory a little bit differently. And so I took that same theory for non-resonant ones and resonant, and I did the same thing with the regular off-center fed, the resonant one. I said, well, let's just chop off the extra short wire, and we'll just use the coax, just like we're doing with the non-resonant bullet antennas.
Yeah.
And guess what? It works perfectly. And now a guy that's got a lot that's 100 feet by 40 feet can now fit in straight an 80 meter dipole, so to speak, because it's 95 feet of wire. He puts the choke at the 40-foot mark, and bingo, he's on 80 meters, where he couldn't do that before at all, because with the end-fed half wave, he's got to have 133 feet, or the off-center fed, he's still got to have the same amount.
Okay, well, yeah, thanks for your help. I'll let somebody get in there. I want to make it clear that Mike's program here doesn't actually calculate impedance. All it does is calculate where the even and odd quarter wavelength multiples are.
That's right.
So, it's not NEC or something. Okay, thanks.
Right, back to the Palomar program here. We're all waiting here. Barry, how we doing in the chat?
We look good in the chat. It's mostly just comments.
No questions?
No questions.
Well, there's one from Danielle. How does a coax feed to be wrapped tightly through the choke? Or can I wrap the coax 4 to 3 inches, the diameter loop?
Yeah, if you, for example, if you have large coax, RG213 or LMR 400, the loops are going to be, 8 to 12 inches. It's not the length of the loop or the size of the loop that counts. It's the length of the ferrite. So in this case, the ferrites are about 2 inches long. They got about a 1-inch hole in them. But if you have large coax, all right, what you need to do is either get a large ring, a 4-inch ring with a 3-inch inside diameter, and put your coax through 5 or 6 times, just like you see in the pictures with a small coax. Or you can take those snap-ons like you see in the picture, and your LMR 400 will go through there 3 or 4 times, depending upon the brand. So what you do is you make three loops going through it, and then you have a completely separate one with 3 loops, and you put the ferrite on that. And those 2 impedances add just like resistors. They'll double, all right? And that will be enough choking to stop the current from going any further down to your radio. What you want to do is make an electrical and stop sign so that the outside current stops as much as you can. With the small coax, it takes 5 or 6 turns through that 1-inch snap-on to do the job. All right, that gives you a roughly 25 dB of common mode rejection, whereas 3 turns gives you about 18 to 19, and you need another 3 on that to actually stop it.
Okay, Carlos, you have your hand up?
Yes. Some thoughts and comments to improve on this excellent presentation tonight. Remember, if you are going to install the wire, could be the NFET half wave or the non-resonant, horizontally. The higher you install it from ground, the better, because you will take a better angle of radiation for DX and 2 main lobes, like on a regular dipole. The lower you go, then you will have an NVIS antenna. The beauty of the Palomar design with the bent downward radiator or counterpoise is that you have that vertical element that will have a great DX performance. Also, remember that as you go up in multiples with this type of antennas, the radiation pattern is going to be kind of crazy, like a clover, because there will be multiple lobes. Your energy is going several directions and several takeoff angles. Probably you won't notice any reduced performance on the higher bands, but you will experience some poor propagation on the higher bands because you are lower to the ground, and that is essentially an NVIS antenna. But this is a very good take, a very good combination, combining the non-resonant part with a choke at some point, like the 42 feet, and also the bend on the radiator will practically is like a half square if you take a look at it from a wider perspective. That's my 2 cents to add up to this presentation. And thank you everyone for your participation.
I'll comment on that. 2 things. One is the NFET half-wave antenna is voltage fed. And what that means is all the current's in the middle. It's not at the ends, all right? And so the max radiation is in the middle of the wire versus ours, which is with the max current is in the where the impedance transformer is, but it splits in both ways. And so and that's why you get a good vertical radiation pattern if you have the coax vertically, for example. And so it tends to work real well doing that.
Yes.
And it works better than the NFET half waves.
And your suggestion is to install the matching unit higher, and
Yes.
if it's a sloper, install the matching unit high in the air and the wire going down.
Yep.
I've seen many hams install the choke or the matching unit on the ground and the wire going up, and that's, to me, makes no sense, because then if your coax is on the ground, and that will add up to ground losses.
See, if you have an end-fed half wave, that's how you do it. Because the current's in the middle, right?
Exactly.
There's no current in the ends, and your coax does not radiate, right?
Yeah.
If they have a choke on it. And so they have to do it that way to put it on the ground. We used to
Yes.
put them on the ground too, but then people would lose a lot. They would gain a lot more just by raising it up.
Exactly.
Okay, hang on.
Thank you, Bob.
Robert,
thank
hang on.
you.
Give me a moment.
Okay.
All right, Robert, go ahead.
Yeah, so I have a question that dovetails right in with that, but in the opposite direction. And I actually brought this question to in advance here. It wasn't prompted by anything said here. So going back to the true end-fed half wave, for a single band, the current is in the middle, right?
For all bands.
So, okay, I have an end-fed half wave on 20 meters, 33 feet long. It's actually a par end-feds for 20 meters that I've had forever. I've used that successfully in a vertical configuration, both at home suspended from a tree and portable suspended from a fiberglass mast, a 12-meter fiberglass mast. I always rig it up for simplicity with the box at the bottom, the transformer at the bottom, and the other end at the top. And now people haven't addressed this particular situation, but I've come across people and posts or videos on the web that talk about what you were just talking about, getting the box higher. And my claim is that in that situation with the single band and fed halfway and the current in the middle, it doesn't matter that the box is at the bottom.
That's right.
Okay. That's what I wanted to confirm.
No, that's
all
correct.
sorts of possibilities with multi-bands and different patterns and current on the coax and so forth. But in the true end-fed half wave, that current's in the middle. It's not going to matter which way is up.
Exactly. I had one more comment too on the previous guy. The when you're using any antenna that's longer than a quarter wavelength or half wavelength, what you'll find is, and particularly on our 71 footers and our long ones, the lobes do split just like you have in a wagon wheel, for example. However, you get gain. You get about 3 to 4 dB gain in the entire transmission. So I have found that I'm sitting on FT8 and I'm working a guy in Europe and I'm calling CQ, and then a guy from Hong Kong calls me, or somebody from South America, because it's split the lobes, and I don't have to turn my log periodic like I used to. I just sit there and work them, and they're all over the different places because I'm getting enough gain in different directions, 360 degrees, that I can actually work more people than I can if I have my tri-bander or my log periodic going to a specific location, because I miss everybody on the side and behind me. So I have found that the end-fed half wave, the longer ones, actually enhance the capability of the number of cues that you can have in a certain time frame, or the number of interesting people you talk to, because you're not specifically directing it to a geographic region. That makes sense?
Yeah.
Can I ask a question?
Well, got your hand up, or you got hit the.
I'm sorry, I couldn't find it. Eric, WA1SXK.
Okay, go ahead.
Yes, I just wanted to see if I have this clear. Robert, you just mentioned also, and Bob agreed with you, is that if you're forced to feed low with your matching network with your coax, you're sloping up, let's say up into a tree, then the better choice, Bob, I guess you're saying, is definitely the end-fed half-wave antenna. Do I have that part right?
You have to place it low. It's a better choice from it's not a better choice if you want multiple bands, but if you have a single band one, yes, it doesn't really make any difference. But because the current's in the middle, you want the middle to be as high as possible. You know, whether that's sloping down or sloping up, it doesn't really make too much difference, does it? If you put it up, and because the current's in the middle. However, if you want to have multiple bands, more than 40, 20, 15, and 10, for example, and you want, or different work bands, then yeah, it makes sense to have it high versus having it low.
Okay, I'm interested then in just one band, trying to get operating on 160 as best as I can. And I guess also you mentioned I'll get some gain. And if I cut it to, let's say, half wave for the 160 band, 160 meters. And also, let's see, what was the other question I had? Oh, did you say that's kind of an omnidirectional antenna, or does it radiate in the direction the wire is going? Is there like a lobe that stands out most? Because I can actually put it in a couple of different directions.
Well, on 160-meter antennas, it's real interesting because you can never get them high enough to have the classic two lobes, even on a dipole, unless you got it up 100, 120 feet, something like that. When you have it low, okay, it's going to be, the radiation pattern is going to be like a big bagel. It's going to be 360 degrees and the takeoff angle is going to be high, right? The higher you have it, the lower the takeoff angle becomes. And that's true of most antennas, including the in-fed half waves as well as our antennas. What you'll find is that even our 71-footer that works 80 meters is good. It's really good out to maybe 300 or 400 miles, right? But when you get past that, you have the same problems that everybody else has with low antennas on 80 meters. You got to have some height on the thing in order to get it, or have a good vertical radiation component, which ours would have because you're using the coax or a separate counterpoise wire. You would have good radiation a longer distance. When you just have a straight antenna, either a small sloper going up or down, you'll find on the fundamental bands, it's pretty much like a big bagel. It's a 360 degrees. As you get higher in frequency, like on 20 meters, you'll have 4 lobes, for example, and they'll be at basically 90 degrees to each other and about 45 degrees to wherever the antenna is pointing. And so, and the higher the bands you go on 10 meters, you're going to get 8 lobes, right? And they're all going to be a little bit less power, but you get power in all directions. And so you'll be picking up people on different bands that you normally wouldn't get with a lower antenna. You're getting some gain.
Okay, thank you.
I'd like to share a rule of thumb.
I just muted you, Carl. We don't jump in here. You got down at the bottom of your screen, you got a heart that says react. You hit that button and it will raise your hand. If you want to speak, please raise your hand. Carlos, go ahead.
Yes, thank you, Dan. When Bob showed the SWR plots on his designs, you can observe varying SWR readings throughout the bands, and those are real world readings.
Yep.
When you have an antenna that shows a flat SWR with a 64-to-1 or a 49-to-1, all from 80 meters to 10 meters, that, to me, in my opinion, is a very inefficient antenna. In other words, a dummy load. So one very important thing to take note, when you see an antenna that has a broadband response with very low SWR, suspect inefficiency. When it's the opposite, like on the Palomar designs, you can for sure know that is a better design, all from the 40-meter band to the 10-meter band, or the 80-meter band to the 10-meter band. So always keep that in mind. Again, thank you, Bob.
Thank you. Can I comment?
Yes.
Part of that is because, well, the design is different than most everybody else's, but when we make our it's very difficult to make a 49-to-1 if you use the classic things that are on the internet. All of our baluns and ununs do not use toroids. They use beads. And you may be familiar with that if you've ever looked at a solid state linear amplifier. There's usually 1 or 2 columns of beads in the final. And they're either 2, 3, 4 beads in a row, and they're sandwiched together somehow. and then the coil is put through the beads. All right. So in our case, for example, for the 100 waters, we use binocular cores with 2 holes in them. We put one turn in there for the primary, and then a second turn. Actually, you can do half turns with beads. You can't do that with the toroids. We use 2 half turns for the balun, or we use 1 full turn for the Unun. And now I get and you can see this on our website. Now I get a flat 4-to-1 with a 200 ohm resistor on it from about 150 kilohertz almost to 100 megahertz. It's flat, but it's not flat with an antenna on it. But
Yeah.
you got to have a flat balun or Unun to start with in order for it to be good with the antenna you're trying to match with it.
Yeah.
We got so good at doing baluns and Ununs that way that we got a good reputation for it. So I said, let's add some wire to it and let's do some innovative designs like the 80-20.
The problem is that many hams are misled by the
Oh yeah.
specifications, and when they see that flat response from 80 meters through 10 meters, they always exclaim, wow, this is an excellent antenna. What a beauty. Folks, that is not a good antenna. That is an inefficient antenna. When you have varying SWR readings on the different bands, like the Palomar design, you can rest assured that is a better design antenna, a lot more efficiency out of it than the one that exhibits a flat response across the whole bands. That's my opinion, at least my experience. I've been a ham for almost 50 years now, and I don't know what's going on in the industry, but many manufacturers are misleading the ham radio community, especially the new folks that are not good at antenna theory and transmission line theory, and they are purchasing those antennas, having very poor results. So let's wake up and at least understand the theory and try to separate what is a good antenna from the ones that are not good antennas.
Okay. Good advice there. Good advice there.
Yes.
I might, I'm just sitting here. Okay, Dave, SBE, look like you're up next.
Yeah, I just wanted to make certain that people had noted the stuff that I had put in the chat about using RG8X tightly wound on ferrite cores. That's a really bad no-no because they have a minimum radius bend of 2.4 inches on RG8X. And the reason is because it has foam insulation. And if you wind that tightly on a core after some number of months or a couple of years, what will happen is the center conductor will migrate through that foam and short out against the inside of the shield, or at least it will lower your voltage ability. And I had this problem. I did this to myself accidentally by using RG8X to wind a bunch of FT240 cores on a quad that I built. And now when I run 500 watts, it arcs. So please do not buy baluns made by anybody, even Palomar, that uses RG8X that's tightly wound on a core. And they do have some of them on their site, but they'll work just fine to start off with. But after a few months or a couple of years, they will start to arc out on you if you run high power through.
Yeah, if you run high power, that's true. Use RG400 or something. You want to run high power. It's got Teflon inside instead.
Exactly. Mm-hmm.
Yeah, most of the ones on our site, people are using between their transceivers and their linears. That's what they're using them for. So they're running 100 watts, 150 watts through them. They don't use them for the high powered stuff.
Well, but you do have them listed as 1.5 kilowatt.
Yeah.
So
they actually will.
Right, and the other thing to note about that too is that if you're actually running 1500 watts, you need a 5 kilowatt rated system, and because the 1.5 kilowatt PEP is rated at an SWR of 1-to-1, and so if you have any SWR in your system, the peak voltage is going to be higher than that, and you'll blow it up. So you should have 5 kilowatt rated stuff if you're running 1500 watts.
And it's made by MFJ.
Okay, Robert, looks like you're up next.
Yes, another question, different angle this time. Looking at the diagram of your bullet end fed OCF with the transformer up on a mast or a pole, if I understood correctly, the first section of coax down to the choke is part of the antenna system that's radiating on the outside of the coax, right?
Correct.
In that event, if you're suspending the transformer from a metal mast, that coax is running down right next to the mast. Would that be an issue, just like running any wire antenna next to a piece of metal?
Yeah, I would keep it, I would either sway it to the side, because I do the same thing. I have a 2-foot standoff on the top of my tower, and that's where
Okay.
I put the matching unit. And instead of having the coax going straight down, I bring it out about 5 or 6 feet at an angle, and then I secure it there, and I have no issues with that at all. It works just
Okay.
fine. It tunes up exactly the same, but no, you don't want it right next to the tower itself per se. It'll couple to it.
Thank you.
Very good comments, and that's a very common problem. Charles, you're up next.
Okay, thanks, Dan. Bob, a quick question. You had mentioned having some customers that used the antenna inside New York City apartment buildings.
Yep.
All right. I live in New York City, but I have a private house on Staten Island on a very small lot. The lot itself is 95, basically 100 feet by 25. But the area that I can actually put any type of antennas is the back of the house to the back of the property. So that's 55 feet by 25. And using a 4-section Roan 25 as like an anchor point right up next to the house, which antenna configuration and length would you suggest to be able to get as many bands as I could, especially if it's like 40 and 80? It may not be doable at 80, so I'll have to live with that, but what would you recommend?
Well, I would probably use our 80-meter ones too. Our 80-meter end fed off center fed's a little too long. That's 95 feet. So I would probably go with the 71 footer. The non-resonant 71 footer, bring it out 55 feet and then just make it go to the left or the right, the extra 16 feet. And then, have it come out, have the coax come out a few feet from the tower. And then just put the choke at the 42-foot mark. You'll be able to work everything from 80 through 6 with that one, except 60.
Okay,
it should tune just fine.
And put the Unun at the top of the tower at 40 feet.
Exactly.
Okay. All right,
Yep.
thanks.
Okay, I see questions in chat. Barry?
Yes, Howard wants to know if a carbon fiber mast will work okay with the off-center fed antennas.
Yeah, I've had no reports of it not working. The metal antennas, if you strap the coax to them for support, for example, is not a good idea. But I've not had any negative results from those types of masts.
Okay, and Matt wants to know if you have any recommendations for books to dig deeper into the Unun balun design, and a favorite book or 3 on antenna design. You mentioned that Palomar builds their Ununs differently using Mix 6, for example. Would love to understand about how the design decisions, lots of good books on these topics have existed over the years, but so many of them seem to be no longer in print or easily available. So any recommendations?
Well, there are several authors out there that when I inherited the company, I inherited the design, and they weren't very popular at the time, but they certainly have proven popular now. Most of the solid state linear amplifier designs all use the two columns of beads, and they show in a lot of detail how to make 4-to-1s, 9-to-1s, 16-to-1s, and all those different types of things, because the impedances they have to match. They usually have a driver transistor or a quad feeding 10 or 12 ohms, and then that's going up to 50 ohms or even more, and then they're bringing it back down again. because that's the impedance that the transistors will work at. And so that's where I went initially, was just I looked up articles on linear amplifiers and how they were winding those. And most of those all have single turn primaries or 2-turn primaries, and then multiple turns after that. And ours are very similar to that. We don't publish the designs of those things because and for a good reason. Everybody says, "Oh, that design never will work," and so you guys you're designing stuff that doesn't work. But 20,000 baluns later in Ununs, I say, "No, I don't believe you anymore." But my voice is only so loud, and so we put them out. You can measure them. You can do whatever you want. You can open it up and take a look at it, see how we did it, and do it that way. But we haven't published any books on how to do it. I'd say the closest one is most solid-state linear amplifier design publications will have it in it. Some of the old CQ magazines, some of the old ARRL specialized publications. I can't remember the name off the top of my head, but they had quite a few of those experimenter designs in there, and we've used that same technology in what we have, and it also keeps the labor cost down significantly. If you try and make a regular 4-to-1 with 2 toroids and number 14 enameled wire with insulation on the outside, and have to space it around there exactly perfectly, take you 4 or 5 hours to make that thing efficiently. And ours take maybe 45 minutes because we're using so much less wire and our bandwidth is much wider, right? And we can take much more power in the same space. I have a balun that's as big as my fist. It'll take 500 to 700 watts digital with 2 beads. All right, nobody else can do that. They're using mix 43s or some other mix of ferrites because that's what all the books say. Well, we use the really low permeability ferrites because they'll take a hell of a lot of power in a very, very small space. And because we don't have a lot of windings to induce inductance and stuff in it, it'll work just fine. So we've been able to get a lot of power in a small amount of space and up our duty cycles, so that one that's rated 500 watts, I've run 500, 600, 700 watts of RTTY through those things, and they don't get hot because the load is correct. If you put the wrong load on there, or you try to use a band because the antenna's the wrong length and fix it with your tuner, yeah, they're going to saturate. I mean, MFJ has that problem all the time. Their 1500 watt has one little bead in it, and that's it. And we use 8 beads in ours. There's no way ours is going to heat up and have that kind of problem. And they're using the cheap mix 40. They won't even tell you what mix they're using, and their engineers won't either. And so we try and engineer right from the beginning. And you're welcome to take a look at them. Most of the kits that we sell, the 4-to-1s, 9-to-1s, are just the classic kits. And we'd rather not give away all our trade secrets, so we don't publish them or show the insides and stuff. I hope that answered your question.
Okay.
All right, everything is good now.
Okay, Barry, thank you. I'd like to apologize for going as long as we have. People, only 1 or 2 have dropped out. It tells me this is a very interesting presentation, worth going overtime with here. And love it. Bob, you're doing a great job for us.
Thank you. I enjoy it.
You look like you've been doing this a lot of years and you're still having fun.
I'm still having fun. I've been a ham since 1963, and when I was 13. So it's
you and I have been around about the same period of time. Well, you accomplished more.
I just wanted to buy a company and have fun. That's really what it's all about. So I help people every day. We put thousands of antennas out there. We solve lots of RFI problems, and people now can enjoy their ham radio station more because they have a happy wife and they have neighbors that aren't complaining to them all the time.
Very important, everybody. And I might comment to everybody here. I had a problem with my antenna design here. I called Bob up for what a solution for one of his products because I have a broadcast station a couple of miles from me here, which was a big concern. He addressed the whole thing. This guy, if you got a problem, give him a call or send him an email. I think he could help you out.
Yeah, we have a LA station here called KFI, and they buy typically every month 50 to 100 RFI kits for AM broadcast, and they give them to their neighbors, and their technicians go out and put them in because they have 50,000 watts, and anybody within about a mile of theirs has got all kinds of interference type of things. You know,
Yes.
because the electronics these days, you know, they're supposed to be under 30 megahertz. They're supposed to be RF proof, but they're not, or the components are taken out. And besides, the rules are never the rules up to this year probably have never been enforced. They just let it go and deal with something else. So our RFI kits help solve those types of problems.
Well, your product has certainly helped me out all through the years here. Okay, Barry, one last chance for you.
We're good at chat. Thank everybody for coming.
Yes.
Fascinating.
Oh, this has been a great one, Bob. I hope to have you back soon. Appreciate you very much for coming on here. Thank you, Dennis. And Lisa, for your help in getting Bob on here. This has been great. I want to, unless we got some more hands pop up or more questions, I am going to pull the plug, say 73s, and we'll see you all tomorrow night.